Okay, so here's where we were last time. We were talking about the implicit function theorem, and about the last thing that we did was we drew this picture, and we made the observation that while for many points, if you're on a level set of some function, then nearby it'll pass the vertical line test. Obviously, it's you got to exclude parts of the surface way over there. But looking at nearby points, very often, yeah, sure, you can choose to view one of the variables as a function of the others. Okay, but sometimes you also clearly cannot. And the analogy is quite strong with a single variable case. The point is that if there is a problem such as we see here, what that problem is that the surface is in the process of kind of wrapping under itself. Right, you can trace this argument through, et cetera, and we did that last time, so I'm gonna leave that to you all to review. But the punchline is that if there's a problem, this should be 0. Partial of f with respect to z should be 0. And how we actually use this result, this result is in some sense the opposite of what we need. This presupposes that we know whether we have a problem. Usually it's the opposite. We're trying to decide if we have a problem. So we take the contrapositive. And the contrapositive of this statement is if this doesn't happen, namely if that partial derivative is not 0, then that means, so if that doesn't happen, then that means we don't have a problem. So this is the implicit function theorem. Now I want to draw your attention to one fact about this. You'll notice that how I've wrote this example here, I used familiar choices of variables, namely x, y, and z in their usual arrangement, right? And that was for kind of the convenience of, so it'll look familiar while we're trying to pay attention to, geometry and calculus, etc. Right? Let's pay attention, though, to the punchline, though, and that is that whichever variable you want to view as being a function of the others, that's the one with respect to which a partial derivative decides it. In this case, if we want to view z as a function of the other variables, okay, take the partial of f with respect to z. Okay, all right. And you then will notice that that's written in this, so the more general version of the theorem here, I wanted to be able to talk about in different variables. I can't call them x, y, and z anymore. We run out of letters, right? So notice, though, that whichever one you want to view as being a function, you want to view xi as being a function of the others, okay, take the partial with respect to xi. All right. Okie dokie. So now let's talk about how to actually compute. Suppose I'm looking at a surface like this, and I use that term flexibly, right? Is that a surface? That's in dimensions. What is that thing? Right? So suppose you have this equation representing whatever in n-dimensional space, and you would like to view, let me say it this way. Suppose you would like to compute this partial derivative. Okay. How are you going to compute that partial derivative? Well, the first thing I have to observe is that in order to decide if this even makes sense, I've first got to decide, is this a function? Remember, you cannot take the derivative of a bicycle, right? So establish that the thing you're trying to take a derivative of actually is a function first. So how would I decide if xi is a function of the other variables? Well, I would have to take the partial of f with respect to xi. Okay, all right. So assuming that's all fine, how are we going to actually compute this partial derivative? Let me skip the algebra up there for a moment, and let me come down here to this, and let me, for the moment, scratch this off. We'll come back to that in a second. So here's our scenario. We've got f as a function of several variables. That was our given. Right? We're further given that we're going to set that f equal to a constant. By setting f equal to a constant, we create a scenario where we can choose to not view all of these, initially independent variables as all being independent. Because I choose to set f equal to a constant, I can choose to infer that for example, maybe xi is a function. And what is it a function of? Well, it's a function of the other variables, as we discussed. Right, let's go back to here. It's a function of the other variables. So just to make my diagram complete, let me come back down here. We'll get to the algebra in a minute. Let me just write down what would our diagram look like representing xi as a function of the other variables. And, well, it would go like this. Let's see here. I'll use... So x1, et cetera, et cetera, et cetera. Now, conspicuously missing is xi. It's not we're not viewing it as a function of itself. That's silly. Right? The point is it's a function of the other variables. So with xi, again, conspicuously removed, it's a function of, everything else. All right. So with that in mind, we are now asking, I remind you, understand, with the constraint that f is 0, what's the partial of xi with respect to xj? So I would like to know, I said that wrong. I would like to know the partial of xi with respect to xj. Okay. So I would like to know the partial of that. That's how xi is a function of, among other things, xj, and specifically that's how changes in xj would propagate up to, directly cause changes in xi. So that's what I'm looking for. The foot in the door on this, to figure out what that is, keep in mind, we don't know what this function is. I don't have that explicitly given. I have not solved for xi. After all, this is the implicit function theorem, not the explicit. If there was an explicit function, take the derivative. Nothing to it. Okay. So we're going to come at this indirectly. We're going to say, well, let's start by taking the derivative of f with respect to xj. Let's consider all of these paths through which changes can propagate. One of which will be the one that we're interested in, right? Et cetera, et cetera. There's lots of different ways that. That we have that f could inherit changes from xj. Let's write all those down, and you get this great big monstrosity up here. That's all of those different paths, and again, just you can look at them. You can see here's the x1 path, here, et cetera, et cetera. Here's the xi path, et cetera, et cetera. There's just all these different paths. Okay. Good news. This is going to simplify dramatically as follows. Keep in mind, we're taking a partial derivative. Partial derivative means that I want to view xi as a function of all these different variables, and I want to view most of them as being constants. All of them I'm going to view as being constants except for xj. That's what a partial derivative is. Right? So, well, look, if x1 is a constant, then that x1 likewise also a constant. So most of what we have in this expression just all constant. And so most of these terms disappear in a puff of smoke. Let's look at that first one. The very first term in the chain rule. Partial of f with respect to x1. And then, okay, now wait a minute, partial of x1 with respect to xj. Well, x1 is constant. That partial derivative is 0. So, that's not 0 factorial, that's 0. Right? So, that term just, poof, gone. Likewise, most of the other terms are gone. Okay, I want to hit the pause button on this before we go on. Is everybody following the point that, because we're looking at this partial derivative, it is automatic that these variables are all constants, and therefore most of these terms just disappear. Everybody happy? Okay. Right. Okay, so there's only two terms that don't disappear. There's this term, and there's that term. And those are real easy to keep track of. You can see them right here. that blue term, the term where xi is your intermediate variable. There it is. And then there's this term where xj is the intermediate variable, and that one simplifies really nicely. I appeal to your intuition. The rate of change of xj with respect to xj is 1. Right? So that's an easy one. Everybody happy with that? Yeah, so there you go. The thing we were interested in, here it is, partial of xi with respect to xj. Again, our strategy was, if you want to compute this thing, compute first an expression that involves it, and then solve for it. And solving for it is pretty easy algebra right there. Okay, so that's how that calculation goes. It's two things. First of all, it's an important thing to understand about how the implicit function theorem works. It's also a really nice exercise in thinking about being careful. What's a function of what? What's playing what role at what stage in the calculation? Right, and going through. All right, so now I want to show you a different point of view on this. Different point of view is to say, forget about all this business that we just talked about, and let's just think through directly, if you will, with the understanding that we're taking these partial derivatives. It does remain that all these other variables are constant, right? Xj is changing. We want to know how xi changes as a result. Partial derivative means everything else is constant, right? So we're just going to ignore all the rest of it. And I'm just going to point out that there are kind of sort of two paths from this picture by which xj can cause changes in f. One is it can do so kind of directly, right? Xj can cause changes in f. Sure. But, oh gosh, excuse me. Here's the other one. Our premise here is that xi is a function of xj. So let's just go down here and observe that, look, if xi is a function of xj, then, well, xj can cause changes in xi, and those changes in xi can also cause changes in f. So you get the same two terms. It's kind of a easier, it's a little, I don't know, sloppy, arguably, right, because we've got arrows going sideways here. But this is just a shorthand for what we had previously written down. But I think it's a little easier to digest, arguably. You can kind of just see, look, this is what those paths look like. I mean, why make a bigger, messier picture, you might say. Okay. All right. Let me now also call your attention to this minus sign. This is a very important minus sign. If you get this wrong, that's not a sign error. If you get that wrong, it's a dramatic, catastrophic faceplant, huge mess up on the problem. Let me explain why. The reason for that. A lot of students misunderstand and think that these things are just kind of individual things. And you can treat these expressions like fractions, and you can just go through and do fractional cancellations, etc. And a lot of people say, "Oh, well, look, we're just going to cancel the df's, and then the denominator of the denominator becomes the numerator." And so, what minus sign? I don't know what you're talking about. That right away, this expression without the minus sign, shouldn't that be partial of xi with respect to xj? Right. So, what's wrong with that argument? What's wrong with that argument is the premise that these things are well-defined things standing alone on themselves. That is simply not the same thing as that. Please do not think of these things here as being fractions of otherwise well-defined things. They just aren't. So let me point specifically. I mean, what am I talking about here? When you write this down, I mean, it does arguably, except for the limit, I suppose, it kind of represents a thing, but it represents a thing in a certain scenario. That says, I'm going to view f as being a function of all these other variables, and I'm going to hold all the others constant. This thing presupposes that xi is constant. This is considering a completely different scenario. So, no surprise, different scenarios, these things are going to have different values and different, they're just going to do different things. Everybody see what I'm talking about? It is representative of a fundamentally flawed and frankly shallow point of view on these things if you view them as fractions and cancel accordingly. The evidence of which would be the elimination of this minus sign. Everybody see what I'm talking about? So be ultra sure that you put that minus sign in there. If that minus sign's missing, I'm going to have a very unsympathetic grading set of grading rules that will apply. Okay, so you've been warned. Pause for questions. Okay. Alrighty. So, quick example. Suppose you want to look at this surface. This is some sort of a surface. Can't draw it. Can't solve for x, by the way, notice. That'd be pretty hard to solve for x. And so let's see here. Can I view x as being a function, even though I can't explicitly solve for it? First question. And if so, what is that partial derivative? Now, before I answer this question, I want to call your attention to another, just kind of a heads up, FYI. In practice, day in and day out in the real world, very often the question will be phrased like this. Very often the question will be phrased as, hey, what's that partial derivative? Right? And it's a little bit of a sloppy phrasing of the question, right? But in the real world, don't just assume that the person who's asking you questions has created a nice, safe, nothing could possibly go wrong here scenario in which for you to do your work, right? So the question kind of presumes, without evidence, that x actually is a function of these other variables, y and z. You may not just assume that, just because the question seems to, right? So again, that's just kind of the way it is out in the real world, the real academic world. So your job then, when you see one of these questions, first, whether it's written or not, this is always implied, implicit. Sorry, bad pun. The implied question is, can I view x as being a function? You've got to answer that first. And of course, the way we answer whether one of the variables can be viewed as a function is we take a partial derivative with respect to that variable. Compute. Not zero. So no problem. We can proceed. You've got to do that first. Otherwise, you have no evidence of whether what you write following this is or is not garbage. Yeah? Everybody good? All right. So next part of the question, what is that partial derivative? Well, we can use the formula from the previous page. The formula from the previous page, roughly speaking, says, well, let me just write it down. It's take the partial of the original f, first with respect to the variable you want to take the partial with respect to, and then divide by the partial with respect to the variable you're viewing as a function, and don't forget your minus sign. Right? Okay. So you write that down, and it's very plug and chug from here on down. Whoops, here we go. I guess I'll have to zoom out. These partial derivatives, the partial of f with respect to z, well, there's your f. Take its partial with respect to z. There you go. Negative x. Partial of f with respect to x. Well, again, there's your f. Take the partial with respect to x, and there you go. Okay. All right. Everybody okay? One last little warning, and I know anyway, last warning, I promise. Some students think that it is acceptable to not do this because, well, isn't it sort of an immediate protection that had this thing been zero, that thing would make a denominator that's 0, and so I would have found out after the fact anyway. Right? And I'm aware of some high school courses where this is considered acceptable policy. And I just want to point out that this is just not acceptable. The reason why is it's not a question of getting answers. It's not a question of getting answers most of the time. Here's an example where it looks like, yeah, that ought to give you fair warning, right? But, I mean, how do you know that there's not going to be some sort of a cancellation or something that's going to make that 0 disappear? Furthermore, and really more importantly, if this were 0, the problem would not be just that you'd be writing down, or you would have to worry about whether you're writing down an answer that's wrong. The problem that this system does not defend against is that you would definitely be writing this down, which is definitely garbage. Again, it's not about the answer, it's about your reasoning, and this reasoning is garbage if that partial derivative is 0, because x isn't even a function. You cannot take a derivative of a bicycle. Yes?
If they just ask you for the partial derivative of x relative to z, but don't give you a point, like the question you were saying,
then you'd
how
leave.
do you figure out whether the partial of f relative to x?
Then you would have to say, you'd have to put sort of a ... after here and say this is valid only at points where the following expression is not 0. Yeah. Right, but you wouldn't be able to give a 100% yay nay. Which, by the way, think about it, just like on a circle. On a circle, sometimes you can write down the partial of y with respect to x, and sometimes you can't. Right? Yes.
Did you plug in the point that they gave you to find the partial?
Yeah. So the way I at the given point. So since we're looking at this point 1, 2, 3, these numbers go into this expression.
But then at the top, when you're trying to find out whether or not it's a function.
Oh, yep. Oh, yeah. So it's
Before?
it's in this step right here that I plugged in the point.
Okay.
Yep. Okay. So enough of that. There's a lot of subtle ideas, by the way, in implicit differentiation and the implicit function theorem. So, be careful. And, again, make sure on the exams, I emphasize it's not about the answer at the bottom of the page that you put in a box. If that's numerically correct, okay, that's nice and all, but I'm looking at your reasoning. I'm looking at, whether or not your reasoning is legitimate and whether or not your reasoning is effectively communicated and complete. So you've got to give me all of this stuff. And I always emphasize this. And it always remains that I'll get some students that'll just go straight to that. And that's not good enough. By quite a bit. Okay, all right. No, I really got to move on now. Okay, so next subject, directional derivative. So this is 13.8. So first a reminder, one of our big interpretations from the chain rule was that the Jacobian matrix is the relationship between input velocities and output velocities. That was again, my favorite point of view on the chain rule, you might say. I don't know, I have several. But a really important point of view on the chain rule is it's a relationship between input velocities and output velocities. And I think it's pretty believable. Let's not get too rigorous about this, but just kind of cancel the DTs, and that's actually kind of okay in its result. It's also a relationship between input changes and output changes. Input differentials and output differentials. Okay. All right. So, quick observation to make is that this is a matrix multiplication, but if we're looking at a real valued function, then this matrix is just a single row. I just, look at the formula for the Jacobian and you write out the various partials. If there's only one output, there's only one entry in each column. So definitely there's only one row. Okay. Furthermore, don't forget that the rows are gradient vectors. And that reminder, that's just the definition of a gradient vector, is it's a vector whose that's made up of the partials of the function with respect to all of the input variables. So, there it is. So, punchline then, if you're looking at a single row matrix that you're multiplying by a single column vector, that's just a dot product. It's literally, that's how you compute that matrix vector product. That matrix vector product is just a dot product. So there's a nice special case then of how to rewrite the Jacobian rule for the chain rule with Jacobian, how do you want to say it? In the special case of real valued functions is that dot product with the gradient vector is how you convert input velocities to output velocities, or again, if you prefer, depending on your situation, input differentials to output differentials. Okay. All right, so heads up for both. Both of these are useful. The Jacobian matrix, dot with the gradient vector. Either way, same thing. Okay. So another way to say this, and just kind of a picture to draw, but the gradient vector, keep in mind the gradient lives inside of the domain. Right? The gradient is what allows you to convert input changes, whatever they may be, input, rates of change or differential changes, whatever, converts input changes to output changes. So in this context, the gradient vector really plays fundamentally the role of, what is a derivative relationship between input changes and output changes. So I think that's worth dwelling on for a moment. Okay. Okay, so we're going to define a new expression now. This thing has its uses. It's called a directional derivative. I want to first observe that it is, I'll use orange. This thing that I'm about to define is its gradient dot vector. Right, so that directional derivative that we're defining, it's gradient dot vector. Right, so fundamentally, it's pretty immediately clear. This is going to be representing some sort of change in the output, appropriately interpreted. So, we're thinking in terms of output changes. In fact, it's just straight up the output change. The asterisk, the one little micro asterisk, is this presupposes if your input change is a unit vector. And I've got a few things to say about that little constraint. So the term directional derivative applies only if your input velocity is a unit vector. Okay. So that being the case, assuming that your input is a unit vector, then directional derivative, it just means rate of change of the function or differential change of the function, depending on your context. It's just gradient dot that input vector. Okay. Now, before I get into the why, notice also the notation. So this is the notation for this thing called a directional derivative. Again, assuming that we have a unit vector input change. Capital D for derivative, I like to think, or directional, depending on your preference. Right? Notice that the input vector becomes a subscript. That's just notation. The function whose gradient you're taking, you're right there. And of course, to get an actual value, you've got to plug in what point are you applying this. So, in parentheses at the end, putting a value. That's our standard notation for. And don't forget to plug in a function, a point into the function. Okay, so that's just notation. All right, so what's the deal with this unit vector business? Why unit vectors? And there's a couple of different cases that can be made for this. One is semantical, and that is, look at the word. The word says direction right there in the word. And how do we represent directions? Keep in mind, a vector is a direction and a magnitude. Magnitude is distinct from direction. So ideally, it sort of semantics suggests that direction kind of means there should be no magnitude. What would a vector with no magnitude be? And unit vector seems like a reasonable choice. So that's kind of a semantical justification, and whatever. It's also going to turn out that this special case, the fact of the input vector being a unit vector, is going to allow some interpretations that are useful, and that's nice. I do want to point out, though, that you should not view this as being an improvement, straight up, full stop improvement on our previous idea. It remains that with no constraints at all on what your input vector is, no constraints at all, it remains that dot product with the gradient gives you output changes. So you might call this the chain rule, right? The chain rule is much more general than what we're calling here the directional derivative. Okay. In fact, just a heads up, and this is a cultural point, a lot of people, when they say the word directional derivative, they actually mean this. So this is a little bit horrifying, but the word directional derivative, the meaning of that term is not universally agreed upon by the entire scientific community. And that's uncomfortable, right? So, it's a state of affairs. So, side note, I mean, in my experience in math, anyway, I think more people use the term directional derivative generally as directional. Yeah, I mean, so look, you're moving with some input velocity, and we want to know what the corresponding output velocity is. This is really kind of the more common interpretation, in my experience, more common interpretation of the term. So, how does this affect y'all? Two things. In Math 212, we're sticking with the book's definition. So, this notation, this term in this course means unit vector for the input velocity. Okay. And then once you get out of this course, a heads up. Just be aware that there's sources of confusion out there. And if someone says directional derivative, you should say, pause. I'm sorry. What do you mean by that? Are you applying that? Is that a unit vector only thing? Are we just talking about the chain rule here? In which case, we just need clarification. Okay. So sorry for the awkward ambiguity. Pause for questions. Yeah.
How can a differential piece of vector be a vector?
So differential does not mean infinitesimal. Differential just means change, right? So think back to single variable calculus. Dx doesn't mean infinitesimal at all. Dx means, if I were to change the input by some amount, what would be my linear estimate of the change in the output? And so differentials just assume that you're doing linear approximations. Yeah, common misunderstanding. A lot of high schools out there pushing this idea that there exists something called an infinitesimal. Not really. That's a kind of a fib that gets told in high schools very often. It can be made sense out of in a way, but what remains, and this is very important, is that even if someone does make some abstruse definition that's not nonsensical of infinitesimals, they are not real numbers. That is 100%. There's not real numbers. So, So anyway, if some of y'all might be a little unsettled by this and kind of thought that I thought derivatives were defined with infinitesimals. I thought integrals were defined with infinitesimals. That's a mistake. And something to clarify, something you want to get straightened out as soon as possible. Side note, I have a video that I recorded this summer called What is an Integral? It's on the YouTube channel. It's in the miscellaneous topics. And there's kind of three big points that I talk about in that recording. And one of them is, what's the deal with infinitesimals? So I encourage you all to give that a listen if you're not entirely clear on that. Or come talk to me in office hours, either way. Okay, great question. Thank you very much for that. Okay, how do you think about directional derivatives? And the first observation, as I already made this observation, is it's a special case of the chain rule. The chain rule says, suppose that you're moving with any velocity in the domain, whatever that might be, and what's the corresponding change in the output. And chain rule applies broadly to any possible input vectors. So here, the directional derivative, the special case is that we're simply going to restrict our attention to unit vectors. unit vectors pointing in any possible direction, of course, but strictly only unit vectors. So special case of the chain rule is one way to think about it, and that's nice. Another way to think about it is that it's a generalization of the idea of a partial derivative. Reminder, what is a partial derivative? A partial derivative, I mean, again, let's not think of it in terms of slopes temporarily. A sort of domain-specific point of view on partial derivatives is that you're moving a la a unit vector in the direction of an axis. Unit vectors, but again with the further restriction that we're moving parallel to an... Oh, sorry, I did not even that way. Just these two, right? So partial derivatives are sort of a restriction, and again, directional derivatives allow for more different directions. Okay, so generalization of a partial derivative, special case of the chain rule. And those are both nice ways to think about directional derivatives. Okay. All right. So, a couple of neat observations. Things that you can do with the directional derivative. Why, again, I ask, rhetorically, why would we do such a thing? Why would we define a whole new term and a whole new notation of something that I've already dealt with in these terms even more broadly? Right? What's this buying us? Well, there's a couple of good answers to that question. The first is, I claim, we're going to prove this momentarily, you can think of a directional derivative, switch colors, you can think of a directional derivative as being rate of change with respect to distance. I'm going to call that df ds. Y'all are accustomed, I think, to the idea that s can represent distance as you move. We do not previously have that concept, right? We've got the idea of df dt, like if I'm moving with a velocity in the domain, velocity with respect to time in the domain, and what therefore is the corresponding output velocity, that's derivative with respect to time in the target. What's derivative with respect to distance? This is a pretty natural thing to want to talk about. If you're climbing a mountain, how steep is the mountain? What's my rate of change of altitude with respect to distance traveled? Very relevant information, right? And if someone were to say, if you were to say, hey, I would like to understand this mountain better, and if someone were to come back and say, okay, well look, you got to tell me how fast you're moving. You tell me how fast you're walking, and then we'll talk about how much the altitude you're gaining. Right? Okay, well, there is this thing called how steep is the mountain, independent of how fast I walk. And I understand that if I walk faster, I gain more altitude faster. And if I walk slower, I gain altitude slower. That much I get. I just want to know the rate of change of altitude with respect to distance. Very natural thing to want to talk about. Okay, we can compute this by a little clever move. It goes as follows. Suppose I have some vector given to me, velocity vector. Keep in mind, velocities, dx dt, have kind of two parts to them. There's a unit vector defining the direction, and then there is this scalar, which is the magnitude, which in this case, being its velocity, the magnitude is the speed. Okay, so I'm just breaking down, my supposed velocity vector into these, unit vector and magnitude, like that. And let's take this equation. Take this equation, and let's just dot both sides with the gradient vector, and let's see what comes out. So dotting with the gradient vector, you get this, and notice, gradient dot v, I already know that that's the rate of change of the output. That's df dt, unavoidably. We already knew that. We also knew previously that v, namely speed, is ds dt, rate of change of distance with respect to time. Also old news. That's what speed is. Right? So look at the nice punchline then. This thing, all right. So this thing, which note is the directional derivative, gradient dot unit vector, In order to make the algebra, the single variable chain rule work out, this kind of has to be ds. This is df ds, namely rate of change of the function with respect to distance. That's cool. All right, so that's why this is true. It's an important interpretation of directional derivatives. Directional derivatives give you rate of change with respect to distance. All right, and as I've already suggested, if you want to know how much the function changes per unit distance traveled, then in the graph setting, that's rise over run, aka slope. So there's a really kind of morally equivalent interpretation. You might say this is the perspective specific take on the previous observation, but nevertheless, pretty nice that the directional derivative is the slope of the graph. Everybody on board with this? Any questions? Is everybody happy? All right. Okay. So a couple of examples. Suppose you're given temperature as a function of position. Now, again, multivariable functions can represent lots of different things. Notice here, we can't draw a graph. I cannot draw a graph of temperature as a function of 3 position variables. That's a 4-dimensional picture. I couldn't dream of it. Okay. But it's extremely relatable, right? I mean, extremely relatable. We understand that as you move to places where sometimes it's a little warmer. Maybe by the window it's warmer. Maybe by the air conditioning vent it's a little colder. Of course, temperature is depending on position. And in this very relatable scenario, reasonable question, suppose that I am moving in a particular way, right? By the way, again, pretty relatable. That's kind of what we do in this life as we move. Our position is given by a function of time, right? Extremely relatable scenario. That said, I can still want to know what's the rate of change of temperature with respect to position. Right? Again, I know how fast I move. I understand that if I move faster, there's more change. Got it, right? But that's all about my own personal experience. I might want to know something other than my own personal experience. If I want to understand the temperature function itself and how it behaves in a certain direction, it makes sense to talk about the rate of change with respect to distance. And it doesn't make sense to talk about rate of change with respect to time because the function itself is unaware of my existence. The function temperature as a function in this room does not care that I'm moving. Right. Okay. All right, so how do you compute dTds? Well, thanks to the argument on the previous page, dTds is the directional derivative. Directional derivative dot product. Now again, the rules are that's got to be a unit vector for that to work out. Okay. So I just need to take a dot product of the gradient vector with the unit vector that's moving in the unit vector that's pointing in the direction that I'm moving. And now I appeal to your geometric intuition. We know that x prime is the velocity vector. The velocity vector is moving in the direction you're moving, right? But with a magnitude, unit vector pointing in that direction, you divide by the magnitude. Yeah? Happy? Questions? Feel free. Yeah?
Shouldn't, we're talking about this like in terms of velocity?
So x prime, this x prime vector right here is the velocity, my velocity in the domain, right? So that's the velocity of, this parametric curve. Yeah. Is that? I'm not sure if that's what you were asking.
Or a displacement.
So the question that we're asking here is to find the rate of change of the function with respect to distance, right? So we don't want to presuppose that we know what our displacement is. Right, again, so I'm kind of looking for something, I'm looking for information about the function that's intrinsic to the function itself, who has never heard of me and does not care how I'm moving, right? And that is what this is with that compute. Did that answer your question? I wasn't sure. Okay, cool. Anybody else? All right. Okay, another example. Suppose, same function, same, temperature as a function of position. Suppose that I'm just given explicitly a velocity, and I want to know dt dt. This is just an observation, and how useful this is for you, for your consideration. But it remains that I could answer this question, dt dt, by writing this down and observing that, now I know my speed, right? I mean, my speed is, well, you can see it right there. It's the magnitude of your velocity vector. But then capitalizing on the fact that that dt ds is a directional derivative. But furthermore, it's a directional derivative in the direction of a standard basis vector. Right? It's a directional derivative in the direction of a standard basis vector. It's a partial derivative. And so, again, depending on your perspective as to whether this is worth it, but we already know that partial derivatives are really easy to compute. World's easiest derivatives to compute. Okay. So another way to compute dt dt. Let me pause on that as well. Okay. All right. So, quick observation I want to make about directional derivatives again. So don't assume that just because we're defining it after the chain rule that means that it's necessarily superior to the chain rule. It's just it's a thing. It has its moments of usefulness, right? But it's not. I'm certainly not suggesting that there's some sort of moral imperative that henceforth, if you want to compute df dt, that you should compute df ds first and then multiply by ds dt. I'm not saying that at all. I am pointing out that sometimes you might find that convenient, I guess. I mean, in this case, it was convenient only because this simplified to a partial derivative, which was only because I was moving in an axis direction. I was moving exactly in the x1 direction. That was unusual. That's non-standard, right? So it's not going to happen all the time. Also, this previous example, sometimes dt ds, namely the directional derivative, is actually what you need. If you want to know the slope of a graph, or if you want to know rate of change with respect to distance, then there the directional derivative is what you want in the first place. So of course it's useful for computing itself. So that's nice. Okay, but here's a big example. I think this is really important. So suppose you've got some function and you're given a velocity, and you want to compute the rate of change of the function with respect to time, not distance. I'm not asking for a slope, right? I want to compute dt dt. Here, notice here are your two options. If you were to compute dt dt using directional derivatives, this thing, you've got to write out sort of the single variable chain rule first, just to get to where you can write down the directional derivative, which, again, you could then subsequently compute. I suppose that's fine. But then, of course, just to be fair, you do have to multiply by ds dt, namely your speed, namely the magnitude of the velocity vector. And in this case, I want to point out there's something really silly about this calculation. Look, I've taken my velocity vector, I have computed the magnitude so that I can divide by it, only to then subsequently multiply by it, and they cancel. This is an exercise in silliness in this case. Why would you do that? Right? It's much easier in this case to just say, well, just use the chain rule. You want to know output change? You want to know the rate of change of the output with respect to time? Okay, cool. Chain rule. Bam. It's a one-liner. Right? So, again, don't feel some sort of moral obligation to do that just because directional derivatives came after the chain rule. Only use directional derivatives if it's either intrinsic to the problem that you've been asked or actually convenient for your purposes. Okay. All right. All right, let's see here. I don't have any time left. Okay, well, this is a pretty good stopping point. We'll call it a day right here. See y'all. Wednesday for the exam. So I want to make sure nobody forgot. So also, real quick, I have homeworks to return. If y'all can stick around for a minute after I finish attendance, I want to pass back all those homework.